Dear students, welcome to the session 1 of module 3 for solid state devices. This session will be handled by myself, Bonifus. In this session, we will be particularly focusing on PN junctions, in which first of all we will be focusing on the equilibrium conditions, in which we will be seeing the concept of contact potential, equilibrium Fermi levels, and space charge at a junction. Coming to PN junctions, mathematics of step PN junctions are simpler. So in this particular area, we will be focusing on step PN junctions because its mathematics is simpler. Actual junctions are greater than step PN junctions. So graded junctions means ND minus NA will vary over the distance on either side of the junction. But if it is step PN junction, this ND minus NA is same if you consider 2 points throughout the junction. There are 4 components of current which will flow across a PN junction. So we have seen those components which consist of drift component and diffusion component, in which drift will be having electron as well as hole. Similarly, in diffusion will be having electron as well as hole component of current. So once you apply some sort of bias, once you apply some sort of bias to the junction, that will increase the value of some of these components with respect to some other components, and which will give rise to some net current flow. At equilibrium, all these components will be having equal magnitude. So your net current will be 0 at equilibrium, but once you apply bias, some of these components magnitude will become larger than other components, and hence we will be having some net component. The next concept we are focusing on is that contact potential. So when we have separate P and N type semiconductor material, that doesn't form a junction. So once you fuse this P and N semiconductor to form a junction, holes will diffuse from P side to N side, and electrons will diffuse from N to P side. So resulting, there will be a diffusion current which can't build up indefinitely because an opposing electric field is created at the junction. We'll see this diagrammatically. We are having separate P and N regions, fusing it together to form a PN junction. So middle will be having transition region, which will contain only immobile ions. Negatively charged acceptor ions at the P side of the junction and positively charged donors at the N side of the junction. And hence you will be having electric field from N side to P side of the junction, because N side of the junction you are having positive ions and P side of the junction we are having negative ions. So your electric field is from positive to negative of ions, or from N region to P region of this PN junction device. Now correspondingly, we can draw the particle flow and resulting current directions. Now, we know diffusion will take place from area of higher concentration to lower concentration. So the black components, this area are diffusion components, and the blue values are drift components. So holes will diffuse from P region to N region. Holes will diffuse from P region to N region. So the resulting current is in the same direction of the hole flow. Similarly, electrons will diffuse from N region to P region. The resulting current is in opposite direction of the electron flow. Now, we said once we form a junction, because of the uncompensated ions at the junction, we will be having an electric field at the junction. Because of that electric field, we will be having drift components. So holes will flow in the same direction of the electric field. Resulting hole current is in the same direction of that hole flow. Electrons will drift in opposite direction of the electric field. Resulting current is in opposite direction of the flow of electrons. no net current can flow across the junction at equilibrium. Current due to the drift of gases and the electric field must exactly cancel the diffusion current. That's at equilibrium. Diffusion current will cancel drift current. Its directions are different, but magnitude is same. Since there can be no net buildup of electrons or holes on either side as a function of time. So at equilibrium, we can write Jp of drift plus Jp of diffusion is equal to 0. Similarly, Jn of drift plus Jn of diffusion is also equal to 0. Electric field E builds up to the point where the net current is 0 at equilibrium. Electric field appears in some region W above the junction, and there is an equilibrium potential difference V0 across the transition region with W. So there is a gradient in the potential in the direction opposite to the electric field. So here we are drawing the energy band diagram of a PN junction. So if we have P region and N region separately, the left hand side you can see your Fermi level will be near to valence band for P region, and your Fermi level will be near to conduction band for N region. But once we join together this P and N regions to form a PN junction, at equilibrium we should have only 1 and 1 Fermi level. So you will be having only 1 and 1 Fermi level at equilibrium. But for P-type material, this Fermi level should be near to valence band, and for N-type material, this Fermi level should be near to conduction band. So we will be having a shift in conduction band and valence band of the N region downwards. So that shift will be equal to Q into V0. Is the difference between P side conduction band and N side conduction band will be Q into V0. Similarly, the difference between P side valence band and N side valence band will be also Q into V0. So a constant potential Vn in the neutral N material will be there. Similarly, a constant potential Vp in the neutral P material will be there. So the difference between these two, that is Vn minus Vp, is taken as the contact potential or V0. The region of width W is called transition region, and contact potential by definition is the built-in potential barrier which is necessary to maintain equilibrium at junction. The contact potential separate the bands as we discussed now. Valence band and conduction band are higher on the P side of the junction than on the N side by an amount Q into V0. But at equilibrium we will be having only 1 and 1 only Fermi level. CFP will be equal to EFM at equilibrium. Now separation of the bands at equilibrium is required to make the Fermi level constant throughout the device. Now we will be finding the quantitative relationship between the contact potential V0 and the doping concentration on each side of the junction, that is Na and Nd. So the drift and diffusion components of the whole current will cancel at equilibrium. So we can write Jp of x equal to Q into Up P of x into E of x minus dp d by dx of P of x, which is equal to 0 because drift component and diffusion components will cancel each other. So the net sum will be 0. So the first term is drift component and the second component is diffusion component. So this magnitude of these two will be equal. So we can rearrange this equation 5 for A like in 5 for B, that is we can write mu P by dP into Ex equal to 1 by P of x into d by dx of P of x. The electric field can be written in terms of gradient in potential, that is E is equal to minus d by dx of P of x. So if we are applying that on equation 5 for B, and if we are applying the Einstein relation, it's d by mu equal to kg by q, we can rewrite the equation 5 for B as minus q by kt equal to d by dx of p of x is equal to 1 by p of x d by dx of p of x. So here what we have reduced that here in equation 5 for B, instead of p of x we have substituted e equal to minus d by dx of p of x. Then according to Einstein relation that we have studied in the second module, d by mu equal to kt by q. So instead of mu p by dp you can write it as q by kt. Then you will get equation 5. Now we will integrate this particular equation from pre-region to end region. Okay. So that's shown over here. We'll be integrating from p to end region. This is minus q by kt integral of vp to en, that is potential at p-region to potential at end region dv is equal to integral pp to pn 1 by p dp, where pp is the equilibrium whole concentration at p-region and pn is the equilibrium whole concentration at end region. Then we'll get this equation, and finally we'll get v0 equal to kt by q as into ln pp by pn, where vn minus vp equal to v0. Now consider that we are having step junction, and at the p side we are having Na acceptors per centimeter cube, and on the n side we are having Nd donors per centimeter cube. Then we can write pp into np is equal to nn into pn, which is equal to Na square, which is same as the equation we have studied earlier, which is n0 p0 equal to Na square. Equilibrium whole concentration into equilibrium electron concentration equal to square of intrinsic electron concentration. As we are having n and p regions separately, for indicating n side we will be using pn and nn. For indicating p side we will be using pp and np. So that's what it is mentioned in equation 5.7. v0 equal to kt by q ln pp by pn. Here instead of pp by pn you can write it as nn by np also you can write, because we know nn pn equal to pp np is equal to Na square. Using that relation you can write v0 equal to kt by q ln pp by pn is equal to kt by q ln nn by np. Okay, now we are assuming p side our doping concentration is Na, and on the n side our doping concentration is Nd. Now for the p side our doping concentration we can write it as Na, and on the n side electron concentration is Nd. So whole concentration Pn will be equal to Na square by Nd. Then in time we can write this particular v0 as kt by q ln Na Np by Na square. Now from equation 5.7, we will be writing pp by pn. From this equation we can write pp by pn. So pp by pn will be equal to e to the power qv0 by k to t. Then as the previous equation explained, that is pp into np equal to pn into nn is equal to Na square. We can write pp by pn is equal to nn by np is equal to e to the power qv0 by k into t. Here we will be focusing on equilibrium Fermi levels. So Fermi level must be constant throughout the device at equilibrium. As we have seen in the previous energy band at equilibrium, we will be having only one constant Fermi level throughout the p in p transition or entire region. Now Pn and pp are given by their equilibrium values outside the transition region. Pn is equilibrium whole concentration at N region, and pp is equilibrium whole concentration at p region. So from the previous equations, it is equation 5.9 in terms of basic definition of pp and pn, and we will be using equation 3.9 that we have studied in the first video, we can write Pp by Pn equal to e to the power q V0 by kT. This equation we have seen just before. Then first module we have said P0 equal NV into e to the power minus EF minus EV divided by kT. So here we are having Pp and Pn. So for Pp we will be writing NV into e to the power minus EFP minus EVP by kT. We have a suffix of P to indicate P region, and for Pn we will give NV into e to the power minus EFN minus EVN divided by kT. And suffix of N is given to indicate it's an entire material. Now rearranging this particular equation, because at equilibrium we have EFP and EFN are equal. So e to the power EFN minus EFP will be equal to, or EFN minus EFP will be equal to 0. So e to the power 0 will be equal to 1. So hence we can write Q into V0 is equal to EVP minus EVN. That means we can prove that at equilibrium P side valence band and N side valence band are shifted by an amount Q into V0. Similarly, if you take the ratio of Nn by Np, you could prove that ECN minus ECP equal to Q into V0. So the Fermi level and valence band energies are written with subscripts to indicate the P side and N side of the junction. Which say diagrammatically. So the P side valence band and its side valence band shifted by Q to 0. Similarly, P side conduction band and its side conduction band shifted by Q to 0. Energy bands on either side of the junction are separated by a contact potential V0 times the electronic charge Q. When bias is applied to the junction, that is forward bias or reverse bias, the potential barrier is raised or lowered. If you apply reverse bias, your potential barrier will be raised, and if you apply forward bias, your potential barrier will be lowered from the value of the contact potential. So the Fermi levels on either side of the junction are shifted each other by an energy equals to applied voltage. Next topic we are going to see is space charge at a junction. Consider the space charge within the transition region is only due to uncompensated donor and acceptor ions. Within the transition region, we don't have any mobile carriers such as electrons or holes. We are having only immobile ions such as uncompensated donor ions and acceptor ions. So just shown over here. The transition region with W. So the edges of the transition region is x0 towards the P region and x0 towards the N region. Now, the charge density on N side is Q times Nd plus. Similarly, the charge density on the P side is minus Q times Na minus. So we can plot it like this. Charge density on the N side is Q times Nd plus, and charge density on the P side is minus Q times Na minus. Now, total charge inside this particular area will be, in the inside is Q plus is equal to charge Q into Nd. That is charge density. That is what we said, Q into Nd. Then area into that length of the transition x0 in the towards the N region. Similarly, the P side it is minus Q into Na. Then area into length of the transition region in P side, that is xp0. Now, we will be assuming that the carrier is completely depleted within the transition region of W, and outside this transition region, that is outside this W region, our P-type and N-type semiconductors are neutral or electrically neutral. So this approximation is called depletion approximation. So in this particular diagram, the positive charge is equal to minus charge by magnitude wise. So we can consider it as a charge dipole. So dipole about the junction must have an equal number of charges on either side. Q plus equal to Q minus. The transition region, that is our W, may extend into the P and N regions unequally. That is the length of Xn0 and Xp0 may not be equal depending on the relative doping of the two sides. Space charged region extends farther into the lightly doped region to cover an equal amount of charge as the heavily doped region. For a sample of cross-sectional area A, total uncompensated charge on either side of the junction can be written as Q into A xp0 equal to xp0 into N is equal to Q into A xp0 and D. This from the previous diagram we can write Q plus equal to Q minus. So in which Q and A terms will cancel each other. And we can write xp0 is equal to xp0 or we can write QA xp0 to QA xp0 to ND, where xp0 is the penetration of space charge region into the P material and xn0 is the penetration of space charge region into the N material, whereas the total transition over W is equal to xp0 plus xn0. Now, to calculate the electric field distribution within the transition, we will use Poisson's equation. So Poisson's equation will relate gradient of the electric field to local space charge at any point x. Or we can write gradient of electric field is proportional to sum of all charges within that particular point x. So we can write gradient of electric field d by dx of x is proportional to sum of all charges. Charges of holes, charges of electrons, charges of donor atoms, charges of acceptor atoms, considering its charges, positive or negative charges. Then we are considering the transition region. So in transition region, we are assuming the depletion approximation. That means within that transition region, we don't have any carriers. P or N is not there. Only acceptor and donor ions are there. So P and N will be equal to 0 within the transition region. So we can write the above equation 514 as d by dx of E equal to Q by epsilon Nd for region 0 to xn0. Similarly, d by dx of E equal to minus Q by epsilon into Na for the region minus xp0 to 0. Now we will be plotting gradient of electric field. So we know our gradient of electric field is opposite direction of the it's in minus x direction. So our electric field is always negative. So we plotted that. So we know Q by epsilon into N, which is positive slope, and minus Q by epsilon, which is negative slope. So we can plot it like this. Okay. N region 0 to xn0, which is 1 by Q by epsilon into Nd. It's positive slope. And in the negative region and in the P region, is minus xp0 to 0, which is minus Q by epsilon, and it is negative slope. And these two will meet at a point which is called E0, which is the maximum value of the electric field. So if x is negative throughout W, since electric field actually points in the minus x direction from N to P. Okay. Now we will be taking the equation 550. That is these two equations, v by dx, q by epsilon to d, and minus q by epsilon to n, and integrating it on the appropriate limits. That's shown here. So first equation we can indicate it from 0 to x0, and the second equation we can indicate it from minus xp0 to 0. And once you integrate, we will get E0 as that's maximum field of that field E0 as minus q by epsilon n d xn0 is equal to minus q by epsilon n xp0. Now electric field at any axis negative of the potential gradient at that point. So E of x we can write as d by dx of x, which is negative gradient of the potential at that point. Or rearranging this particular equation, we can write as rearranging and integrating it. Integrating this particular equation, we can write it as minus v0 is equal to integral minus xp0 into x0 e of x dx. We have it from p region to n region. Now, integral of minus xp0 to x0 e of x, which is nothing but area of the depletion region triangle. That is this triangle, this area of triangle. So, triangle area we know 1 by 2 bh. B will be w, h is e0. So we can write v0 equal to minus 1 by 2 e0 w. Then we have the equation for e0, which is previous, minus q by epsilon n dx. Substituting that, you get 1 by 2 q by epsilon n dx. Similarly, you can substitute for na x v0 also you can substitute. This equation also you can substitute. Now, the balance of charge says that xn0 into nd should be equal to exposure and as we discussed earlier, this region of transition region which is extended towards n side, which is xn0 into the ions over there, that is it. And similarly, region of transition region extended towards p side, which is xp0 into the accepted ions over there, which is na, should be equal. And we know transition region w equal to xn0 plus xp0. Now, rearranging this equation xn0 into nd equal to xp0, we can write it as xn0 equal to w by na plus nd. Then substituting this one, equation 5, 9, this previous equation, substituting it, we will get contact potential is equal to 1 by 2 by epsilon na nd by na plus nd w square. Now, from this particular equation, we will find w. So, w we can write as 2 by square root of 2 epsilon v0 by 2 na plus nd by na. And then again, we can write it as na plus nd by na. You can write it as 1 by n plus 1 by n. Then v0 can be written in terms of doping concentration using equation 5.8. As we know, is equal to kT by q ln na nd by na square. If you substitute that, we will w as this particular equation 2 epsilon kT by q square ln na by na square. 1 by na plus 1 by nd whole raised to 1 by 2. So, penetration of the transition region into p and n materials, that's x0 and xp0, can be written as xp0 equal to w into nd by na plus nd, which can be rearranged to 2 epsilon v0 by q nd by na into na plus nd whole into 1 by 2. So, xn0 also you can write w into na by na plus nd, which is equal to 2 epsilon v0 by q into na by nd into na plus nd whole raised to 1 by 2. So, the next topic we are going to discuss is the forward and reverse bias changes. Till now we have seen the equilibrium junction and its energy band conditions. So, we now will be considering forward bias and reverse bias conditions and relations to the steady state. Steady state means it's a non-equilibrium state in which all the fluids are balanced. So, in which first of all we will see the concept of qualitative description of current flow at a junction, then we will see the concept of carrier rejection. So, we are discussing about PN junction at equilibrium. At equilibrium, we said we are having transition region at the junction, and your electric field will be going from one region to the region of the diode, and we'll be having a potential gradient which is just opposite to the energy gradient. This N side your potential gradient will be higher and P side of potential gradient will be lower, and the difference between these two N and P will be 0. Corresponding the energy band diagrams are P side our bands are shifted upwards and the N side our bands are shifted downwards. We can say energy diagrams or energy is now related with respect to negative charge, whereas potential is now related with respect to positive charge. That's why we are having opposite shifts. And the difference between ACP and ECN or AVP and EVN, which is Q is. Now we have seen that particle flow and current flow directions also. So we are having 4 components: hole diffusion, electron diffusion, hole drift, electron drift. So if you see the diffusion components of the current have the same direction, hole diffusion and electron diffusion components, that's the black arms of the current, have the same direction. And drift components of the current have opposite direction. Both the drift components are having the same direction and both the diffusion components are having the same direction. But drift and diffusion is having opposite direction. So your net current will be 0 at equilibrium because all these 4 components are having equal magnitude. But once you apply forward bias, our middle transition region will be narrow. And the potential requirement, potential barrier at the junction will be lowered. So at the junction, earlier we had a potential barrier of Q into V0, but now we are having a potential barrier of Q into V0 minus VR. And once, as you have applied the forward bias, the Fermi levels will be having a split. It won't be constant again because you are applying a bias. So the shift between these two Fermi levels, EFP and EF, Q into VF. So that value is added to the energy barrier, that is Q into V0 minus V. Our net barrier will be decreased. So as the barrier of diffusion decreased, our diffusion components will be having more magnitude than the drift components. So in forward bias, diffusion component of the current will dominate. Now at the reverse bias of the junction, we will be having a larger transition region. So we will be having a more electric field at the junction. So more electric field means more chance of drift component. And we are having larger transition region means we are having less diffusion of electrons of course. That means we are increasing the barrier at the junction. So correspondingly our potential diagram will be changing from V0 to V0 plus VR, and energy band diagram will be changing from Q into V0 to Q into V0 plus VR. Our energy band is decreased from Q into V0 to Q into V0 plus VR. And if you consider the corresponding current components, our diffusion components will be smaller compared to drift components. And provided if we have some carrier generation at the junction, this drift components will contribute to a large current. Total current crossing the junction is composed of the sum of diffusion and drift components. Electron and hole diffusion currents are both directed from P to N. Drift currents are from N to P. Net current crossing the junction is 0 at equilibrium, since the drift and diffusion components cancel for each type of carrier. Under reverse bias, both diffusion components are negligible. Because of the large barrier at the junction, and resulting current is relatively small. Generation current from N to P. So this is the VI carrier for an ideal diode. So positive direction of the current is taken from P to N. Only current flowing for negative V or negative voltage is the small current, which is otherwise called IGN, due to carriers generated in the transition region or minority carriers which diffuse to the junction. So current at V equal to 0 or otherwise equilibrium is 0 since generation and diffusion currents cancel. So we can write total current I equal to I diffusion minus modulus of I generation, which will be equal to 0 at equilibrium, that is at V equal to 0. Now, if you are applying a forward bias V equal to Vf, that will increase the probability that a carrier can diffuse across the junction by the factor Qe to the power Q into V by Vf by Kt. Similarly, for reverse bias, diffusion current is the equilibrium value reduced by the same factor with V equal to minus Vr. So the diffusion current with applied bias can be written as modulus of Ig into e to the power Qv by Kt. V may be plus Vf or minus Vr. So total current is the diffusion current minus absolute value of the generation current, which is I equal to I0 into e to the power Qv by Kt minus 1. Applied voltage V can be positive or negative. When V is positive and greater than a few Kt by Q, the term is much greater than Upt. That is, its first term is much greater than T. So the first term will dominate. And if V is negative, exponential term approaches 0. This term approaches 0, and minus I0 term will dominate, which is otherwise also called reverse saturation current. Now we will be focusing on the carrier injection. What we are focusing here is that from the P side, when you apply forward bias, holes will be injected to N side, and these holes will be negative, so minority carriers at the N side. Similarly, from the N side, electrons will be injected to P side, and these electrons will be minority carriers at the P side. Minority carrier concentration on each side of a PN junction vary with the applied bias because of the variation in the diffusion of carriers across the junction. Now, equilibrium ratio of hole concentration on each side is given as Pp by Pn equal to e to the power Qv0 by Kt. We have derived it earlier. With bias, when you apply bias, the borders of the transition region will vary. Okay. So instead of Pp, we can write it as P of minus xp0 because it's towards the P region. And instead of Pn, we can write just P of x and 0. And instead of V0, we will be writing as V0 minus P. So P of minus xp0 by P of x and 0, which is equal to e to the power Q to V0 minus V by Kt, where V0 minus V is called altered value. Now, we are assuming low level injection. Low level injection means that we will be considering the changes in minority carriers only. Majority carrier changes we are not considering. So here we consider Pp is the majority carrier because holes at P region is majority carrier, and Pn, that is holes at N region, which is minority carrier. So we will be considering change in minority carrier, or we can neglect the change in majority carrier. So we can write P of minus xp0 equal to Pp itself. Then dividing these two equations, 526 and 527, we'll get it as P of x and 0 by Pn equal to e to the power Qv by K to T, where this P of x and 0 is steady state minority carrier hole concentration, which is hole. Pn is equilibrium minority carrier concentration. Here it is hole. Equilibrium minority carrier concentration, which is also here. With forward bias, minority carrier hole concentration and the edge of the transition region n side increases, then the case at equilibrium value Pn. Similarly, at reverse bias, its equilibrium value, that ratio of the holes or hole concentration at the edge of the transition region on n side will decreases. Now, exponential increase of hole concentration at xn0 with forward bias is an example of minority carrier injection. Now, a forward bias V results in a steady state injection of excess holes into n region and electrons into p region. Excess holes on the n side at xn0 can be written as delta Pn, which is equal to P of xn0 minus Pn, which is equal to Pn into e to the power 2V by kT minus 1. Again, capital delta Pn is the instantaneous initial excess carrier concentration at xn0. P of xn0 is the carrier concentration at xn0, and Pn is the equilibrium hole concentration. Excess electrons on p side at xp0 can be written as capital delta np equal to n of minus xp0 minus np. Here n of capital delta np is initial excess hole concentration at the p edge. Where n of minus xp0 is that electron concentration at that xp0 minus xp0. np is electron concentration, equilibrium electron concentration at p region, which is equal to np into e to the power 2V by kT minus 1. These are based on the equations discussed earlier. As holes diffuse deeper into n region, they will recombine with electrons in the n material, and resulting excess hole distribution is obtained as a solution of the diffusion equation. Here, holes are getting diffused to n region and electrons are getting diffused to p region. So earlier we had derived this diffusion equation and we have found its solution. So we can use the same diffusion equation and the same solution. So the only difference we will be having here is that we will be having a suffix of n and p to indicate n region and p region. Similarly, inject electrons in the p metal diffuse and recombine, giving an exponential distribution of excess electrons. So now we will be defining two new coordinates. That is, we have edges of our transition region. At the n side it is xn0 and at the p side it is minus xp0. Now the distance measured from xn0, which is will be treated as xn, and the distance in the p metal is measured from xp0 will be treated as xp. Now we will be writing diffusion equation on both sides of the junction and solving for the distribution of excess gas. This delta n and delta p, the small delta n, small delta p, will get small delta n at xp, that is electrons are diffusing towards p region. So p equal to capital delta np to e to the power minus xp by ln. So this was the solution of the diffusion equation we solved earlier. So the only difference is that to indicate this in p region, we have suffix of p here. Okay, xp and np. Now np we know, so delta np we know, which is np due to 2v by kT minus 1 that you have substituted. Similarly, in excess hole concentration at n region, that is delta p at xn, capital delta p n due to the power minus xn by np. Again, this is the solution of the diffusion equation of holes in n region. Then capital delta p n you can write as p due to the power 2v by kT minus 1. So that is one more draw here. We are having a Pn region. We have minus xp0 and xn0, middle 0. So the distance which is measured from xn0 in the end region will be treated as xn, and the distance which is measured in the p region from xp will be treated as xp. So in the n region we are having equilibrium Hall function as Pn, and in the n region you are having equilibrium electron concentration as n. Now in the p region, the initial excess Hall concentration is capital N. So your total electron concentration at that point will be Pn equilibrium plus that initial is Pn plus delta. But this capital delta Pn will decay over time. So capital delta Pn stage value will be equal to small letter Pxn equal to capital letter P to the power minus xn by L. Similarly, at the P side, Np equal to capital letter Np plus capital letter Np at the initial value. This Np is constant. This capital letter Np will decay over time. That instantaneous value of axis carries small letter n of xp equal to capital letter Np to the power minus xp by Ln. Hole diffusion current at any point xn in the n material can be calculated from the equation 440 that we have discussed earlier. Earlier we have discussed the current density equation. Here we need to find the current. So the only difference is that current is equal to current density into area. So earlier you have current density equation, to which you just multiply area. You will get current equation. So and we are calculating current at any point xn. So instead of x we are having x naught. Now total Hall current injected to the n material at the junction can be obtained by evaluating this particular equation at xn equal to 0. That is the origin of that xn. Xn equal to 0. So this particular equation we are substituting xn is equal to 0. So IP at xn equal to 0, you will get it as QA dP by NP capital letter Pn is equal to QA dP by NP Pn to e to the power QV by dP minus 1. Similarly, we could find injection of electrons into P material, which leads to an electron current at the junction. So which is In at xp is equal to 0. By similar steps we can solve it, and we will get it as minus QA dN by Ln capital letter Np, which is equal to minus QA dN by Ln Np into e to the power QV by kT minus 1. Now we will be neglecting recombination in the transition region, and each injected electron reaching minus xp0 must pass through xn0. The total diode current I at xn0 can be calculated as the sum of Ip at xn0 and minus In at xp0, xp equal to 0. That is I equal to Ip at xn equal to 0, which is minus In at xp equal to 0. Then you get it as QA into dP by NP Pn plus dN by Ln Np into e to the power QV by kT minus 1, and this first term QA into dP by NP Pn plus dN by Ln Np, we take it as I0, and this is called diode equation, which is having the same form as the qualitative relation we have discussed with the VA current. That is I equal to that Ig into e to the power modulus of Ig into e to the power QV by K minus 1. The same equation. So the diode equation describes the total current through the diode either forward or reverse bias. Now, the current for reverse bias in this particular equation substitute V equal to minus V. You will get this particular equation. If VR is larger than Fu kT by Q, then total current is just the reverse saturation current. That means we can neglect this exponential term if VR is very large. Okay. Then the total current will almost minus I0, which is this term, or this exponential term can be neglected. Or I equal to minus I0. So total current at the junction is dominated by injection of carriers from more heavily doped side into the side with lesser doping. In P plus N junction, NP is negligible compared to PN. Current will be dominated by injection of holes. So here's a forward bias junction with variation of the Cauchy Fermi level is given. At equilibrium we had only one Fermi level, but when you apply a forward bias, instead of one equilibrium Fermi level, you will have a split Cauchy Fermi levels Fn and Fp, and that difference will be Q into Vf. So equilibrium EF is split into Cauchy Fermi levels Fn and Fp, which is separated within the transition region W by an energy QV caused by the applied bias V. If the applied bias is Vf, the difference will be Q into Vf. Forward bias, the depletion region, P into N. We can write just Ni square into e to the power Fn Fp by K. This will be Ni square into e to the power QV by Kg. If the applied bias was Vf, instead of V, substitute it as Vf. On either side of the junction, minority carrier Cauchy Fermi level varies the most. Okay. On either side of the junction, minority carrier Fermi level varies the most. That means at the N side, Fp is varying, and at the P side, Fn is varying. So majority carrier concentration is not affected much. So majority carrier Cauchy Fermi level is close to the original EF. Cauchy Fermi levels are more or less flat within the depletion junction. So the two methods for calculating the junction come from excess magnetic carrier distribution, and the first method we have seen, which is diffusion comes at the edges of the transition region. That means we have a transition region of W, its edges are Xn0 and minus Xb0. Then we have found the current at Xn, that is the distance from Xn0, and Xp, that is the distance from Xb0. Those two edges we have found the current, or simply we have found the slopes of the carrier distribution. Okay, and then, we have found I at Xp0 and Ip at Xn0, and finally we have summed it. So this was the first method. The second method to find the current through the junction is by finding the charge distribution and divide by the carrier lifetime. So charged by carrier lifetime is current, that comes it. So we need to find the charge distribution on the P side and N side, that is delta P and delta N. Then from which you need to find Qn and Qp. So Qn will be that minus Q into A into that 0 to infinity carrier distribution and delta Nx. So delta N of Xp dxp. Then In at Xp equals 0 you can find by Qn by tau. So Qp you can find by Qa into delta P and Xn. Then Ip at Xn equals 0 you can find by Qp by Qp. The diode equation again by summing these two. I equal to I by X0 minus I at Xp. Then we will get the same equation. Okay. So, as a summary, today we have discussed concepts of PN junction. When PN junction regions are formed to form a junction, what will happen? That diffusion component, the current components that we have seen. Then the depletion region with its expression we have seen, contact potential, the concept and the equation we have seen. Then we have seen the concept of space, charge density and the junction. Then we have derived the current equation through a PN junction using two methods, using slope method and the charge method. Thank you.